I will be talking about some collaborative work with multiple people, and I will go through and talk about these individuals at the end of the presentation. So first, I'd like to motivate the topic of this talk, and that's really seeing people. So why is seeing people interesting? Well, first of all, humans are the dominant subject in the majority of images and video online. And with advances in sensor technologies, we've gained many different ways of collecting data to enable us to reason about their behavior. So improved algorithms for understanding human behavior will ultimately lead to a number of socially and industrially relevant applications, such as the ones that you see here. However, seeing other types of applications we've seen at this conference. So industrial quality inspection, humans are very complex entities, and they exhibit very complex behavior. So first of all, they're fully articulated. So their visual appearance is much more complex than the appearance of rigid objects. And secondly, the cognition and self-reflection that humans perform is also highly complex. And this could be dependent on a variety of factors, which involved, other people, objects in the scene, or other environmental factors. About a slightly less intentional gestures. And so the intentional gestures here will be called the ChaLearn Looking at People competition. And so what we mean by communicative gestures is that these gestures accompany body parts are going to be clearly visible and articulated, gestures, and also localize them in time. Now, I'm going to talk a little bit more in detail about this data set because particularly in the multimodal setting. So there's been about 14,000 instances quite animated in the ways that they do gesture during conversation, so it was a good subject group. These were recorded using a Connect sensor, so we have RGB plus D. And what we acquire here are color, depth, and articulated pose streams. There's also been, and this wasn't included as part of this 2014 now, there's several challenges that occur at multiple spatial and temporal scale. This gesture can be basically fully characterized by upper body motion alone. So essentially stationary in terms of the upper body and a role in communicating this gesture. The second challenge, and this is the one I'm going to focus on mostly today, is that we have a number of different modalities. So depth video of the hands, we have this skeleton type of motion, and these somehow have to be integrated. And really it's unclear a priori how to actually integrate these in deep neural networks. So traditionally, before the advent or the popularity of deep neural networks, people typically fused these sorts of modalities at either integrated at the input level or at the feature level, integrated at the level of predictors. So we train per modality predictors and integrate, for example, their posterior probabilities over classes. Now, deep networks, such as the one I'm going to be talking about shortly, allow us much more flexibility in terms of how and when we integrate these modalities, and we can learn arbitrary representations that may assist in doing these modality fusion. So I will elaborate on this architecture a little bit later on. at this problem is that we're from Mark Aurelio Ranzato, and it really shows the 90s and why they're actually working now. It's essentially we have larger data sets, we have larger amounts of compute power, and this has allowed us to scale these architectures that are not fundamentally that different than what we had before. But essentially, the most important factor over the past few years has been scalability. Microsoft COCO or Visual Genome or so let's talk about scales is to employ showing 3 different temporal scales, and each of these architectures are essentially operating in the exact same way. So what we have is a combination of single scale pathways that are connected in parallel, and each pathway is going to learn its own representation, and it's going to perform gesture classification at its own scale. I will give more details about these individual per scale architectures in a few minutes. But the important thing here is that what we're presenting the network is what we term a dynamic pose. And this dynamic pose is really a sequence of video frames that have been synchronized across the modalities, and they're sampled with a given temporal stride. So you'll see we're always collecting essentially, oops, I don't know why I suddenly got music here. Okay, there we go. Always 5 frames which are connected. Spacing is different in each of these channels, but essentially, so looking at any one of these particular architectures, the way it's going to integrate modalities is that we're going to learn modality-specific information first through a number of different layers, and this particular architecture is going to be defined by the type of modality. So for example, for intensity video and depth video, we're going to use convolutional layers. We're going to have a couple of convolution and max pooling layers, and then intensity video and depth video will be fused. And then for the mocap, which comes in as a vector input anyways, we're simply going to learn fully connected layers or deep neural network here, and these are going to be eventually merged in with the depth and video a little bit later on. And then finally, for the audio stream, we're actually going to learn 2D instead of 3-dimensional convolutional nets, and then they will have their representations also fused at this shared hidden layer. So first of all, the depth video stream is really useful. So what we're going to do is we're going to extract a bounding capture that's been provided by the skeleton, and then we're going to subtract the background by thresholding along the depth axis. So we'll apply some simple local contrast normalization, and stream or the skeleton information is slightly more sophisticated in terms of the way that it's pre-processed. I'm not going to elaborate too much on this, the detail, but the details are given in this ECCV workshop paper, and we've continued to use that representation, which works quite effectively in our follow-up works. Now, the important thing here is that we've just extracted 11 joints from the motion capture stream, which are represented in the upper body, and the important that we've done position normalization. So we've represented angles with respect to the hip joint. We've also performed size normalization. So this is taking the angles and normalizing them to be able to compensate for different body size. It's made up with about 100 velocity that are being computed again in the body-centered coordinate system. Okay, so back to the architecture. The difficulty architecture and the amount of labeled data we have available to train it at each of the different temporal scales. And if we're looking at these three different network. Again, we only have about 10,000 labeled gestures to be able to train the network. So if we suddenly just connect everything up, perform gradient descent, and hope that the fusion structure automatically emerges in the weights, we're actually not going to be able to actually structure these weight matrices such that it that works well. And then we're going to use the pre-trained individual modalities. We'll be able to integrate them in a type of late that with iterative training will gradually grow for training such a complicated model. Back to this architecture, what I'm actually picturing at this here and the output layer. So I'm going to focus on the weights that are connecting these different modality-specific representations to this shared layer, and then from the shared layer to the output layer. So I'm going to zoom in on that. Okay, so what you're seeing even with the pre-training, I've already said that if we just drop the output layer and I do direct fully connected wiring, we're going to achieve a very poor local optima. And so we have a high degree of freedom in these in the representations here. So what we propose to do is essentially go and construct essentially a hardwired model that performs a fusion strategy that works reasonably well, and that's the weighted arithmetic mean of the per modality predictions. So each of these modalities, again, are going to be pre-trained to do a gesture classification on their own. So we're going to have an intensity prediction, a depth prediction from each of the hands, a mocap prediction, and an audio prediction. And then these are going to be wired into this shared layer, such that the shared layer is going to be initially representing the individual per modality predictions. Then this output layer is going to take these predictions and combine them in the approximation of a weighted arithmetic mean, or in other words, a standard late fusion. Okay, so just taking a little bit more detailed view of the weights, this W1 that was pictured connecting the shared, individual per modality representations to the shared hidden layer, this is going to be set up in a block diagonal way, such that there's, at the beginning of learning, there's going to be absolutely no cross-modality information. Okay, so there's no crosstalk between modalities. And we're going to divide this layer up into k blocks, where k is the number of modalities. So each of these blocks are going to have n units, where n is the number of gesture classes. And essentially the shared layer here is going to represent the posterior probability of any particular class in the classification, and this will be for the k individual modalities. This second layer is going to be set up to take these posterior probabilities and combine them using a simple weighted average towards the output layer, which will have n units representing the different gesture classes. Okay, so at the beginning of training, we're going to have a simple fusion. And then when we relax the training stage and we'll perform stochastic gradient descent, we will allow the network to learn cross-modality structure. So this matrix will no longer be block diagonal. It will actually, at the end of training, look something like this. So this is actual picture of the weights after training, where you see we do have cross-modality structure, but of course the majority of structure is within the modalities themselves and between likewise modalities. So for example, between the two different hands, we have lots of connectivity. Okay, so using this approach, essentially gradually relaxing the type of fusion from a simple fusion to a more complex fusion, was able to place first in the competition that took place a couple years ago. So the metric here is something called the Jacquard index, which essentially is an intersection over union in time. So it's measuring the ability of the network to be able to classify and temporally localize the individual gestures. And in addition to winning the ECCV 2014 challenge, we also were able to win the OpenCV State-of-the-Art Vision Challenge, which was a vote on which algorithms in particular categories people would most like to see inside OpenCV. Okay, so that was work from a couple years ago. I'd like to then describe a couple of post-competition improvements that we've made. So the first one is a very simple one. You can improve on the performance of this original architecture by simply doing an improved gesture localization. So what we do is just train a binary classifier on motion segments and non-motion segments, and this allows us to take gestures that are poorly localized. For example, in this picture, we see uncertainty in the classes on the pre- and post-stroke phases, and use this binary motion detector to just clean up the boundaries. So it's a very simple improvement, but it gives about 2% on the Jacquard metric. The more interesting improvement that we made post-competition was based on the idea of dropout. So I imagine the majority of people in the room have already heard about dropout and are familiar with it, but I'll just briefly read in this slide. It's essentially something that was introduced as a regularizer in the 2012 now famous ImageNet result. And it's a type of stochastic regularization that just, for every presentation of an input example, drops out a random set of hidden units or inputs. And essentially what this does is it punishes co-adaptation of hidden units. And at the time, at test time or deployment time, we do a model averaging over the possible architectures. We be careful about rescaling the weights. And this can be viewed as a very parameter efficient form of model averaging. So the tweak that we make on this dropout procedure is that we investigate the ability to drop out on a per modality basis. So again, going back to this shared hidden layer, which integrates the different modalities, after we've relaxed this system to allow crosstalk across modalities, we will effectively have these hidden units being computed as a sum of two terms. So the term on the left will be a term that represents modality-specific information. So in a particular unit, it will be initialized in a particular block. This is correlations within the dimensions of an individual modality. And then you have the second term, which is essentially a collection of the crosstalk information or correlations across modalities. And so if we put a multiplier on this second term and we set this thing to 0, that essentially knocks out any of the cross-modality information, and that gets us our original initialization where the model is just performing a late fusion. If instead of using a fixed coefficient, we introduce a stochastic term, which is just essentially a Bernoulli selector variable, we can have stochastic dropout of the cross-modality information. Okay, and so essentially that's what we do, and we train this with some probability of representational modality dropout, and this allows us to punish co-adaptation of units, but also train a network that's more robust to noise within specific modalities, and also drop out, for example, the audio features disappearing for a period of time, which often happens in multimodal setups. So if we look at results with and without the what we call Moddrop, or the modality-wise dropout, we can look at on the top, this is looking at just classification accuracy, so no localization, just on the individual dynamic poses. And then at the bottom, which is the more interesting result, is a Jacquard index on the test set. So just taking full gestures and being able to temporally localize them. So the important points are that we do see a small advantage, particularly in terms of the Jacquard score, when we use Moddrop in addition to dropout alone. But more interestingly is when the modalities themselves are unreliable. So for example, the mocap or the audio or the hands are missing, then we get a considerable improvement using Moddrop compared to standard dropout. And that's to be expected. Okay, so in the next part of the talk, I'd like to discuss some more recent work on the idea of learning fusion architectures. And I mentioned already that typically what's been done in the literature is either fuse very early on in the network, so to take the individual modalities, maybe have some features that are extracted from them, and do a fusion right at the start of the network, and then learn representations that are designed from these multiple modalities. Or we can do a late fusion. So we train individual modality-specific predictors, and then we integrate their predictions at the end. Networks like the one I've already discussed allow us greater flexibility in terms of fusing the predictions, and this, as I showed, using a careful initialization strategy actually is quite effective. However, the issue is that we've put a lot of existing knowledge into this type of network. So we've said, well, intensity video and depth video are like modalities, they have a lot of correlations, and therefore they should be integrated earlier on in the network. And then so after this integration of intensity video and depth video, then we should do an integration of the motion capture and then the audio information. Okay, so we had a very simple architecture here, but it's been designed to be efficient. We have another interesting result that shows actually the effect of doing fusion as we perform training. So on the x-axis here, this is kind of an abstract concept. This is a training stage. So this is the idea of introducing a new modality into the training process. I mentioned before that we could do per modality specific classifiers, and then we could add another modality and begin, use that as initialization, start training again. So this is what's happening on the x-axis. It's something that's discrete. So don't view this as necessarily on a sort of a wall clock or in terms of number of iterations. So what you see here, labeled as 1, 2, and 5, for example, this is an intensity-specific predictor, this is a depth-specific predictor, and this is a mocap-specific predictor. So we see that on its own, motion capture is a much better predictor of gesture compared to the visual information. And then next, if we take the visual information, which is intensity and depth, and we integrate them, you'll see that the error falls drastically to 3, which is video of a single hand. When we take the video of a single hand and we integrate it with the video of the other hand, thus you see the drop from 3 to 4. So again, we get another gain in terms of merging both hands. And then when we take the visual information and merge it with the motion capture, we get another drop to number 6 here. You see that now in terms of number 7, that's audio on its own. It's actually not a great predictor of gesture compared to mocap, but adding the audio to the visual and mocap stream, which is happening at number 8, you see a further a drop in error. And then finally, I've been talking about earlier how we do multi-scale gesture recognition. You see each of these colors here representing different temporal scales, so individual predictors at each scale. Those are finally tied together at step 9, where we bring the different scales together and integrate their predictions, and we get a final drop in error rate. Okay, so again, going back to the issue with this, it works well, but it's a fair amount of engineering in terms of when and how to merge these individual modalities. Okay, so the big question here is, can we actually learn not just the features, but also this modality fusion process? So, several aspects of this modality fusion we would like to learn. So, for example, the order in which the modalities are learned, the depth of the network in where we actually do the fusion, the amount of training we could do in each of these modality-specific representations prior to fusion, the type of training, so we could use different learning algorithms or different optimization strategies for different modalities or different objective functions, and finally, the type of fusion operation. So again, we get different types of fusion being performed, so either in linear or nonlinear way within the network. We'd like to be able to learn this. This is actually strongly related to a discussion that was just posted a few weeks ago, sort of mid-June. There's a blog post called In Deep Learning, Architecture Engineering is the New Feature Engineering. And so there's always been this romanticized notion of deep learning sort of being the end of feature engineering. And certainly feature engineering has decreased with the popularity of deep learning, but what happens is architectures have essentially become more complex. So people are doing more architecture engineering. This blog post actually points to a few recent works, many taking very different approaches in terms of learning architectures. And actually at this conference at CVPR, there's actually been a number of papers that are beginning to look at learning the architecture, which is also related to the model search problem. Okay, so the obvious way to approach this architecture learning problem is, in my opinion, there's two obvious approaches. One is to treat each of these aspects of fusion as essentially a hyperparameter. So Miguel in the talk before me already introduced this idea of model search. I'll just go back to this and just say, with learning there's a number of different hyperparameters. And he pointed out that it's actually very slow to perform this procedure because you have to select a particular fusion architecture, train it to convergence, measure its performance, and then use some sort of meta-optimization algorithm that can take this information and propose a new solution. So I'll give more details on this in a minute. The good thing here is that it conceptually is quite easy, and we have fairly good off-the-shelf tools now to actually do model-based hyperparameter search. I'll describe one of those shortly. The second view, and the more interesting one in my opinion, is proposing a model framework that has a differentiable fusion structure, and then employ gradient-based optimization directly on this architecture. So you're learning both the parameters of the model and the fusion architecture together. So this should be much quicker than approaching it as a hyperparameter optimization problem, but again, this is more difficult because it requires some ingenuity in the design and of both the architecture itself and also the objective function used for optimization. So let's look at the first view, the simpler one. These neural networks have many associated hyperparameters, and any of those that you have worked with neural networks know this. You have to choose a number of layers, the number of hidden units per layer, the learning rate, regularization, and so forth, early stopping. And these fusion structures can be incorporated into this. But how do you set these? Typically, these have been set by expert knowledge. This was already pointed out by Miguel, doing some sort of systematic search, like a grid search or a random search. But more recently, there's been a number of works that have treated this as a more principled problem and explored this in the context of what's called sequential model-based global optimization. There's actually a fantastic review paper that came out earlier this year focusing on a particular family of techniques that have been quite effective that are called Bayesian optimization. Now, to review grid search, most of you again are familiar with this. We discretize the parameters that we want to search over. So for example, we want to search over learning rate, we want to search over the number of hidden units, assuming just a single hidden layer, and we have a coarse grid here of different model structures that we'd like to attempt. The problem is when we start introducing other types of hyperparameters, for example regularization, we get an exponential growth in terms of our search space. So this works effectively for very low dimensional search problems, but it's very ineffective in high dimensions. Random search might be a bit counterintuitive, but it's actually significantly more effective in higher dimensions, and essentially it captures a lot of the practical advantages of grid search. So for example, it's conceptually simple, it's easy to implement, it has trivial parallelism, just like grid search, but it's trading off a small reduction in efficiency for very low dimensional spaces for a huge gain in efficiency in high dimensional spaces. So this picture comes from James Burke and Yoshua Bengio a few years ago, and I really like this because it shows, just for a very simple two-dimensional search problem, how a random layout for your model search can be a lot better than your grid layout. So for example, you have these two parameters, one that's very sensitive to the choice of the parameter choice, and another one that's very, what they call unimportant, so it's not very sensitive. If you perform a grid search where you've discretized each of these parameters, you'll try 3 different settings of the important parameter and 3 different settings of the unimportant parameter. But if you perform a random search, then you actually try 9 different settings of the important parameter and get much more information about the optimization surface. Okay, so again, I'm going to refer you to the review paper on Bayesian optimization, but in one slide, just to give you a little bit of an intuition of how it's working, this example comes from Eric Washu from a number of years ago in a nice tutorial paper. The idea is to actually build a model of how your hyperparameters relate to the score that you care about, which is typically your test accuracy of your model. And so what you're going to do is you're going to initially try a few random settings of the hyperparameters, and you're going to basically have no uncertainty. This is what you see here. We're considering just the case of a single parameter. So you've tried this parameter, for example, your learning rate, in 2 different spots. So you have no uncertainty about how the model performs using that learning rate, and that will give again, this is, say, for example, the test accuracy of that model with that learning rate. But then you have this whole unexplored area where you have uncertainty between these different settings of parameters. And so you have these 2 models that are built. One is this model that maps from this choice of hyperparameter to the test performance. And then you have, as equally important, another function called the acquisition function, which takes this model and proposes a new point to search. So this acquisition function essentially trades off exploiting the information you know about how those parameters worked previously with exploring the space of the unexplored regions. So for example, these purple regions in which you're uncertain about how those particular parameters work. Okay, so you'll see now the acquisition function balancing this exploration and exploitation and saying, at this red point, this is the learning rate that you should try next. So you go out, you train your model with that learning rate, you measure its performance, you add this data to the model, this collapses your uncertainty around these two different points, and then the acquisition function says, go out and try this learning rate. And then you try it, and then again you reduce your uncertainty in that area, and then again your acquisition function will say try this next point, and go forward with that. So that's just a graphical view of how Bayesian optimization works. So if we're actually going to apply this type of model to the search over fusion architectures, we have to deal with the fact that it's actually a discrete problem. So a priori, these different fusion architectures, such as the ones that I have pictured here, in this setting we have 4 modalities that are being merged in some arbitrary manner. These have to be compared to each other in some way, right? To be able to do a search over this space, we need to measure effectively similarity between them. And so we actually have to define our search space as well. So what we've done as a starting point is that we're going to fix the modality-specific front end. So I've already mentioned that, for example, in the Montalbano dataset or the ChaLearn dataset, we have intensity, we have depth, we have motion capture, and we have audio. And so features that are learned by pre-training these individual modalities are represented here by the green boxes and representing different modalities. So once you've pre-trained these modalities, you can then allow the model to select a particular architecture that will fuse these different modalities at a given layer and add fully connected layers. So we've allowed for essentially 0 to 4 fully connected layers to follow each step of fusion, and we fixed the fully connected layers that are added to be constant width. Possible trees that satisfy this generation algorithm and search for a way to compare them. And so when we we can actually take a smaller data set, which is the Kernel activity data set. This has 5 different modalities. This is an activity recognition data set. We can generate all possible fusion trees for these modalities, and we can look at their test accuracy using a cross-validation strategy. Now, if we do a completely exhaustive search, we can actually do this because Kernel is reasonably small compared to the Montalbano data set. We can see there is diversity in accuracy over the different fusion architectures. All right, so there's clearly a sweet spot, but many different architectures give reasonable performance. So I mentioned that a requirement doing a Bayesian optimization over the fusion architectures is having a way to assess similarity between different fusion architectures. And so effectively what we would like to do is we'd like to take some architecture A or architecture X and architecture Y and assign them a similarity score. And so the way that we do this is that we create an undirected graph where each node represents a particular fusion architecture. And then we define edges within this graph as mutations between the architectures. So you can go from one architecture to any other architecture by essentially doing mutations on the tree itself. And we do this by expansion and collapsing these points of fusion. And so then you get this big undirected graph where you have all of the nodes representing all your fusion architectures. And what you can do is you can find a kernel here where your distance is essentially a radial, sort of a smoothing operation performed on the geodesic distance between any 2 nodes in the graph. And intuitively, you look at any 2 fusion architectures, you look at the number of operations that would mutate one into the other, and then you apply something like a Gaussian to that, and that gives you a kernel on this space. Okay, so if we visualize this kernel, what we've done here is we've taken a baseline architecture, so a very simple fusion structure, and on the x-axis, this is the distance of any particular architecture from that, in terms of this geodesic, from that baseline architecture. So you have the architecture itself, you have 1 hop away, 2 hops away, 3 hops away, in terms of the number of mutations you would need to do for a particular fusion architecture. And so each of these blue points are different fusion architectures. And again, the x-axis is their distance away from the baseline fusion architecture. And on the y-axis here, what we're plotting is the absolute difference in test accuracy. So the important thing that you see here is that the kernel is capturing some sort of correlation between distance and as implied by the kernel and the difference in test accuracy. So you see there is a trend that the mean test accuracy increases as you move farther away in terms of the fusion architectures, and the variance increases as well. So if we compare random search to doing Bayesian optimization using this graph-induced kernel, it's early results, but it seems to actually be working fairly well. So we've tested this on the Kernel dataset, and the plot is showing the error of the best architecture found at any particular iteration. So for example, after 8 iterations, we have the error of the best architecture found so far, or after 256 iterations, the error of the best architecture found so far. And we see that using the information gleaned from designing this graph-induced kernel is advantageous over simply doing a random search over the trees, which is using no information about similarity between them. Again, all of the fully connected layers here have 128 units. So if we do optimization and capture the information about, for example, the hidden layers and the units within a layer, this could actually be added into the kernel as well and possibly improve performance. Now, on the Montalbano dataset or the ChaLearn dataset, there's actually, the way that we've designed the trees here, there's less variance than CAD60 in terms of the test accuracies over the different architectures. So both the Bayesian optimization at present and random search are finding a reasonable architecture, or a good architecture in a reasonable number of steps. However, I think the important thing is that we're able to find a marginally better architecture than the hand design architecture in a very quick search, so about 12 iterations. So finally, I'd like to talk about the next stage, which is the second view about learning a fusion architecture. And again, we're starting this now, and I'd like to just describe, we haven't published anything on this, but I'd like to describe the approach that we're currently taking, because it's related to a paper that was presented at CVPR. So I mentioned before these various stochastic regularization methods, which are now pretty ubiquitous. So these have been used widely to regularize structures in deep learning. By randomly removing parts of the network. So for example, we can remove units, and we have dropout. We can remove weights, and we get something called drop connect. We can remove layers, and this is connected to the ResNet architecture, and so forth. There's an interesting paper here at CVPR called Blockout by authors at Google and CMU, and they've pointed out that doing stochastic regularization on, say, a fully connected model implies a particular weight structure. So you can see for dropout, if you do dropout on the units in any particular layer, this is the weight matrix that are connecting two layers, and you permute the rows and columns of that weight matrix, you'll note that you get a weight matrix structure that looks like this. So basically, some units are connected to nowhere. Okay, so white implies that there's their actual weights. Black is that those weights have been zeroed out. If you look at drop connect, you have a much more random structure because individual weights are being knocked out stochastically. Now the interesting thing about blockout is it actually takes units and assigns them to clusters. So you get kind of a tiled structure in the weight space. And what that corresponds to is that by having this tiling on the weight matrix, you can introduce different architectural components. So blockout actually generalizes dropout. So essentially you can have a cluster, say the units in this incoming layer are assigned to the blue cluster, and the outgoing units are assigned to the blue cluster, and then some units in the outgoing layer are assigned to a red cluster. So those are essentially dropped out because they're not being connected. Or you can have units in the incoming layer being assigned to the red cluster, and none of the units in the outgoing layer being assigned to the red cluster, and therefore there's no connectivity from those units, and they're effectively dropped out. But with the blockout approach, you can effectively doing split operations, so you can assign units to multiple clusters, and you can say, so you assign units in the incoming layer to red and blue cluster, and you assign units in the outgoing layer, some units to blue, some units to red. You actually get a split operation, or you can do the inverse and get a merge operation and so forth. And these are the same kind of architectural components that are needed to assemble multimodal fusion architectures. So we're experimenting with that now and look to see some work coming out very shortly. So
The conclusions here is that in designing these very complicated multimodal fusion architectures, careful initialization and gradually permitting more and more effective parameters seems to work very well. It was good enough to win the ChaLearn competition, but still we're not totally satisfied with this approach because it requires a lot of engineering. I talked a little bit about Moddrop, which seems very effective in terms of both regularizing the network and increasing its robustness to missing modalities and noise. And finally, I talked about some early results with Bayesian optimization of model structures. What we have to do now is integrate different hyperparameters into this model search, not just the fusion-related hyperparameters. And finally, I described the work we're doing now on actually learning with stochastic gradient descent, both the parameters and the fusion architecture inspired by Blockout. And that's all. I'd just like to thank my co-authors. Most of the heavy lifting here has been done by Natalia Neverova, who recently graduated and now is at Facebook AI Research. She was co-advised by me and Christian Wolf. Several postdocs and students have been involved in this work, Dinesh and Mikhail from University of Guelph, and we've also been collaborating with Tim and Mohammed at SRI. The last thing I wanted to point out is that we do like to release code on GitHub, so there's a couple of projects recently released of interest. The baseline methods for doing the multimodal gesture recognition, which I described today, have just been released using a Theano and Lasagne-based implementation. And then a few weeks ago, we released a Theano-based framework for doing very easy multimodal, multi-node, multi-GPU parallelization of any type of model in Theano, but we've provided implementations of GoogleNet, VGG, and AlexNet in this framework, and we're implementing RNNs right now. And I also look forward to talking to Miguel about the implications of his work on this sort of large-scale GPU-based hardware acceleration. Thanks a lot.